In this video, we'll look at solving 2x2 systems by the elimination method. Alright, so sometimes this method is also called the addition method. Here you have an example of a system of two linear equations in two variables. And we once again want to solve these equations at the same time. So we're looking for the ordered pair that works for both equations. One thing you might notice about this set of equations is that the x coordinates are opposites of each other. The coefficient for the x in the first equation is +1, and for the coefficient of x in the second equation, it's -1. We're going to begin by combining these two equations together. When we looked at the substitution method, we looked at a way to put our two equations together so that we had one equation in one variable. We're trying to do the same thing, but the method that we use to create that one equation is going to be slightly different. Instead of a substitution step, we are going to use addition, which is why this method is sometimes called the addition method. So I have these two equations written out. Again, I'm just going to label them 1 and 2 just so that we can refer to them if we need to. And I'm going to begin by adding these two equations together. So it's important that my equations are already set up so that the like terms are lined up and the equal signs are lined up as well. So when I add, I am going to add like terms. X minus x, or x plus -x, is 0, so that term gets eliminated, or that variable gets eliminated. For the y's, I have 1y and 2y, which is 3y. Bring down my equal sign, and then -5 plus 14 is 9. So now I have one equation in one variable, and I can solve this equation. So I'll divide both sides by 3, and I have y is equal to 3. So I now have the y coordinate of my solution. My solution, remember, is in the form of an ordered pair. So I could even start to write my set builder notation, the set of all x, y, such that x equals, we need to fill that in, y equals 3. So we'll just find the x value. Oh, the glare is a little off there. Let me move that over. It's a sunny day out today. All right, so we have the y value. We need to go ahead and find the corresponding x value. So we could use this y value in either of the original equations, because remember, the x value will be the same for both equations, as will the y. I'm going to go with the first equation because the coefficient of x is +1. It doesn't matter which equation you'll use. So I'm just rewriting that first equation, x plus y equals -5. Now replacing the y value that I found, x plus 3 equals -5, and then we'll subtract 3 from both sides so that we can solve for x. X equals -8. So we have our y value, we have our x value. The ordered pair would be -8, 3. And if we wanted, we can check that solution, but we would want to, again, make sure that we check in both equations, otherwise there's no point in doing the check. All right, so it's a process of adding the equations together that we want to focus on. So we're going to try that with the 3 examples that you see here. Along the way, we're going to talk about the different things that we have to do in order to be able to eliminate one of the variables. Then we'll kind of think about a general procedure that you can follow. All right, so for number 1, I have x plus y equals -6 and -2x minus y equals 0. So let me go ahead and get that on my page. All right, and I will once again label my equations just to help me keep track of what's going on. So the idea is to add the equations together so that one of the variables eliminates. So I'm going to mentally add these together before I write anything down because we might have to change things. So mentally, if I add things together here, 1x minus 2x, well, 1 minus 2 is not 0, so the x's won't disappear there. Here I have y minus y, and because I have the opposite coefficients, positive and -1, when I add those two together, the term does disappear, the y disappears. which is great. It doesn't matter that it's the y that I'm eliminating. In the last example, we eliminated x, but as long as we eliminate one of the variables. So I'm ready to go ahead and add my equations together. It is important to note that my equations are all set up in standard form, x, y equals constant, so that's important as well. All right, so combining the x's, 1 minus negative 2 is negative 1, so negative x. The y's are going to be eliminated now, and negative 6 plus 0 is negative 6. So now I'm solving for x, because my equation only has x in it. Divide by negative 1, x is equal to 6. So far I have the x coordinate of my solution. I need the y coordinate. So in order for me to get the y coordinate, just like we did with the substitution method, we choose one of the equations and we plug in the x to get the corresponding y value. I'm going to choose the first equation just because the coefficients are a little bit easier to deal with. X plus y equals negative 6, replacing the x value with what I just found to be 6. 6 plus y equals negative 6, and then subtracting 6 from both sides. So we have y equals negative 12. So that means my solution set is the set of ordered pairs, x, y, in this case just one ordered pair, such that x is equal to 6, y is equal to negative 12. All right, so again, in that case, we were able to just add our equations together and the y's canceled out. In the second example, looking at the coefficients, I don't have opposite coefficients for x or for y. If I add the coefficients for x, 1 plus 3, I get positive 4. Add the coefficients for y, 2 plus 3, I get 5. So neither of the variables will eliminate if I just start to add them together. But if you remember, we have some addition properties of equality. We're allowed to add, subtract, multiply on both sides of an equation as long as we're multiplying by something that's not 0. So I am allowed to multiply one or both of my equations by whatever integer or fraction I want in order to make the coefficients opposites. So you have some choices to make. So you have to decide whether you want to eliminate the x or eliminate the y, and your choice might be made by whatever seems to be the most convenient. If you can get away with multiplying only one equation, that's ideal because the less work you have to do, the less room for error. So I see here that my coefficient for x in the first equation is 1, and in the second equation is 3. If I wanted to make the coefficient of x in the first equation the opposite of what it is in the second, I would want to make that coefficient a negative 3, right? Opposite signs. I could easily make that a negative 3 by multiplying that first equation by negative 3. Let me label my equations as well. So I'm going to multiply the first equation. I have to multiply the entire equation. I can't just multiply one term. It's got to be the whole thing because that's the property of equality. So I'm going to put parentheses around this side, indicate that I'm multiplying it by negative 3, and then on the other side, make sure I multiply by negative 3. I don't have to multiply the second equation at all, but I do like to rewrite the entire system. So here my first equation is now negative 3x minus 6y, don't forget to distribute, equals positive 15. The second equation is the same, so I'll just rewrite that one. 3x plus 3y equals 9. Now when I add my equations together, since the x's have opposite coefficients, the x's will cancel out and be eliminated. The y's, when I combine, will be negative 3y equals 15 plus 9 gives me 24. I only have an equation that contains y. I'll go ahead and solve for that y value. Divide by negative 3. So here y is equal to negative 8. Once I have the y value, I can find the corresponding x value. I can pick either of my original equations or any version of them. I'm going to go back to my first equation where the x was has a coefficient of 1, because that will just be a little bit easier to work with. Replacing y with -8. And then solving for x. So x minus 16 equals -5. Adding 16 to both sides, I have x equals 11. So my ordered pair, x comma y, would have an x coordinate of 11 and a y coordinate of -8. Right, so in that case, we had to multiply the first equation by an integer so that we had opposite coefficients for x. The x's were eliminated, we solved for y, we used that y to get the corresponding x value for the solution. Let's take a look at the last example. In that last example, you'll also see that neither of the coefficients for x or for y are opposites, and we also have some fractions to deal with as well. So let's take care of both of those things. If I don't like the fractions, I can get rid of them. If I don't mind the fractions, I can keep them. It's entirely up to you. I'm going to multiply the second equation by 4 to get rid of the fractions. This is just to get rid of fractions. You could skip this step. Rewriting both equations. First one and the second one. First one staying the same right now, 2x plus 5y equals -3. And then the second one, 4x plus 5y equals -2. So now I see that the coefficients for y are close to being opposites, but they have the same sign. So I just want to change the sign of one of those y values. It doesn't matter which one I change the sign of. I'll just go with the first one. To change the sign, I need to multiply by a negative. So I'll multiply both sides of that first equation by -1. So I have -2x minus 5y equals 3. And for the second equation, 4x plus 5y equals -2. Now combining, I have 2x equals 1. And then I'll go ahead and solve for x. Dividing by 2 on both sides, I have x equals 1/2. All right, so let me go ahead and find the y value that goes with this. I could use either equation to find the y value. Maybe I'll stick with the first equation because the coefficient of x will cancel out that fraction. So maybe it'll help me avoid some fractions there. So looking at that first equation, 2x plus 5y equals -3, replacing the x with 1/2. All right, 2 times 1/2 is 1, so 1 plus 5y equals -3, subtracting 1 on both sides. 5y equals -4, and then divide by 5. I have y equals -4/5. So this ordered pair has fractions for the x and for the y coordinates. So this would be an example of why I don't want to have to graph, because finding that point and identifying the coordinates would be a little difficult if I were graphing by hand.